Welcome back. Today we're going to be taking a look at topic 1.8, rational and integral exponents. So again, let's get started by looking at our learning targets. In a previous lesson, we looked at how to express a power with a rational exponent as a radical and how to convert from a radical to a power with a rational exponent. We're going to review that in this lesson, and we're also going to look at applying the exponent laws to simplify expressions and then solve problems involving powers or radicals. So before we get into our lesson, let's just do a quick refresher of our exponent laws. When we're multiplying powers with the same base, we can add our exponents. When we're dividing powers with the same base, we can subtract our exponents. When we're raising a power to a power, we multiply our exponents. Remember that if we have a product that we're raising to a power, we can distribute that exponent. And the same thing for a quotient, we can distribute that exponent. Now, any number or variable raised to the exponent of 0 gives us a value of 1. And remember that a common convention in math is that we try to give our final expression with positive exponents only. So if I had x to the negative m, that can be written as 1 over x to the m. If I had 1 over x to the negative m, that could be written as x to the positive m. And then fractional exponents or rational exponents, my denominator becomes my index. So I have the nth root of x to the m, so that can be underneath the radicand, or the m can be outside the brackets. So using those laws, let's just do a quick refresher. We have 36 to the 1/2. Remember that my denominator becomes my index, so I'm going to have the square root of 36 to the exponent of 1. Remember that with square roots, we don't actually have to write our index, so we can just write root 36. And if we're asked to evaluate, that would give us 6. If I have 4 over 5 to the negative 2, I'm going to start by flipping that fraction, so that's going to give me 5 over 4 to a positive 2, and then I can distribute that 2 to both the 5 and the 4. So that's going to give me 5 squared over 4 squared, which is 25 over 16. And in the final review question here, I have 1 over 3 to the negative 3. When I bring that power to the numerator, my exponent becomes positive, and 3 cubed is 27. Example 1 is going to give you a number of different examples using exponent laws and converting from fractional to exponential form. Now, all of these questions can be checked with your calculator, but we want to try to work towards an exact answer. And sometimes we may end up with an irrational expression, and so we don't want to just rely on our calculator. We use our calculator to check our work, but I want you to be able to demonstrate that you can show how to get to the answer and how those laws can be applied. Feel free at any point as you're working through these examples to pause the video, try them on your own, and then check your work. For part A, I have 9 over 16 to the negative 3 over 2. I'm going to start by reversing that fraction. So I'm going to have 16 over 9. That will give me a positive exponent. Now I can't do 16 to the 3 over 2 in my head, but I can convert this to a radical expression. So my index is 2. That's going to give me the square root of 16 over 9. And I'm going to choose to put the 3 outside simply because I can do root 16 in my head easier than I can do 16 cubed in my head. So the square root of 16 is 4, and the square root of 9 is 3. And that's going to leave me with an exponent of 3. 4 cubed is 64, and 3 cubed is 27. So checking these on my calculator, I can go 9 over 16 to the exponent negative 3 over 2. And then I can do 64 divided by 27. And for B, I have negative 8 to the exponent negative 2 over 3. Again, I'm going to reciprocate that fraction, so I'm going to have negative 1 over 8, and that gives me a positive 2/3. Again, I'm going to convert this to a radical, so my index is 3, and I'm going to have negative 1/8 as my radicand, and then I'm going to square it. If, again, you wanted to square your negative 1/8 first, you could do that. Remember that when you're squaring a negative, you should get a positive. So the cube root of 8 is 2. So the cube root of negative 1/8 is going to be negative 1/2. And then negative 1/2 squared is going to be 1 over 4. Taking a look at C, I have 3 to the negative 2 and 27 to the 1/3. These are not common bases, so I cannot use my exponent laws. However, one option that I have is to actually evaluate 27 to the 1/3. So I have 3 to the negative 2. And 27 to the 1/3 is the cube root of 27. So that leaves me with 3 to the negative 2. And on the bottom, I have 3, which would be 3 to the 1. Now these have a common base, so I could use my exponent laws. Negative 2 minus 1 is negative 3. And 1 over 3 cubed is 1 over 27. So one option is to see if there's a way to get them to have a common base, and then I can combine them. Now another approach might be to look at the negative first and say, hey, I need to deal with that. So I've got 3 to the negative 2. I would move that into the denominator. I still need to evaluate my fractional exponent. So I've got the cube root of 27. There's nothing on top, so that means I'm going to have a 1. That will give me 1 over 9 times 3, which is 1 over 27. Different methods, same answer. So moving on to example D, we're in the same situation. We have two powers, they don't have the same base, so we're going to evaluate first. Since these are fractional exponents, I'm going to convert them to a radical. So that's going to give me the cube root of negative 27, all squared. Again, I've kept the squared out simply because I can do this math in my head easier. And then I've got 4 to the 3 over 2. So I'm going to do the square root of 4. This time I'll maybe put the 3 inside. Again, it doesn't matter which way you approach it. The cube root of negative 27 is negative 3. Again, those brackets are important. Now 4 cubed is 64, so I'm looking at the square root of 64. Negative 3 squared is 9. The square root of 64 is 8. So that's going to leave me with 72. For E, I have two powers with the same base, so I can combine using exponent laws. So 5 over 2 plus 7 over 2 is going to be 12 over 2, and that leaves me with x to the 6. Now for F, I have a to the 1/2 divided by root a. These are not written in the same form, so I either want to convert a to the 1/2 to a radical or root a to an exponent. In this case, I'm going to convert both to exponential form. So I'm going to leave the numerator as is, and in the denominator, root a is the same as a to the 1/2. So when I have a to the 1/2 divided by itself, that's going to leave me with 1. I could also look at this and say a to the 1/2 minus 1/2 is a to the 0, which is also 1. Taking a look at G, we have the cube root of 8a cubed b to the 6th. There's a couple different ways that we can approach this question. One is to convert this to exponential form. So that's going to give me 8a cubed b to the 6th, all to the exponent of 1/3. Now, 8 to the 1/3 is the same as the cube root of 8. A cubed to the exponent 1/3, 3 times 1/3 would be 1, and 6 times 1/3 would be 2. Now the cube root of 8 is 2, so I'm going to be left with 2ab squared. Another way to approach this is just to deal with the radical. So I'm going to take the cube root of 8, but I'm going to write it as 2 times 2 times 2, and then we have 3a's and 6b's. Now when I'm taking the cube root, that means I'm looking for groups of 3. So there's a group of 3 2's, there's a group of 3a's, and I have 2 groups of 3b's. And for every circle, I'm going to pull out a value once. So I've got 2, I've got a, and b times b would be b squared. Now remember again, if you want to check your work, you can absolutely do that on your calculator using substitution. So I'm going to give a value of 2, and I'm going to give b a value of 3. Now checking my work, I'm going to do math for 8 times a cubed times b to the 6th gives me 36. And if I go 2 times a times b squared, I also get 36. So again, you can use substitution to check your work. Moving on, for h, again, we have powers with common bases. So I'm going to have x to the 3 over 2 times x to the 1/2 is going to give me x to the 4 over 2. And y squared times y to the negative 1 is y to the 1. Simplifying, this leaves me with x squared times y. And finally, we have 4a to the negative 2 times b to the 2 over 3 divided by 2a squared b to the 1/3. So 4 divided by 2 is 2. Negative 2 minus 2 gives me negative 4. And 2/3 minus 1/3 is 1/3. Again, we want to leave our final answer with positive exponents. So this is going to be 2 times b to the 1/3, all divided by a to the 4th. These are both in exponential form, so you can absolutely leave it like that. You may also choose to convert the b to the 1/3 to a cube root. So we'd have 2 times the cube root of b divided by a to the 4th. Now remember that little shortcut I showed you earlier. If I have a squared and a to the negative 2, and I know that a squared is bigger, I can subtract 2 minus negative 2, but then I have to remember that that is in the denominator. So we're going to finish off this lesson with a word problem. Now we've looked at these same types of word problems in a previous lesson, so hopefully this will be a review. I want to remind you that when we're working with word problems that have formulas, it's really helpful if you try to identify where those numbers are coming from. So where are we getting the 2000? Where are we getting the 2? In grade 10, a lot of the times these formulas are given to you, but as we move on to other levels in high school math, you're going to be asked to build these equations yourself. So the sooner you can start to recognize those patterns, the easier it will help you as you move forward in math. Example 2 says a culture of bacteria in a lab contains 2,000 bacterium cells. The number of cells doubles every day. The relationship can be modeled by the equation n equals 2,000 times 2 to the t. When we're working with a formula, it's always important that we identify what our variables represent. So n is the estimated number of bacteria cells, and t is the time in days from the moment the experiment began. Generally, when we're working with formulas, it might be helpful to list our variables. So part A says how many cells were present after 1 week. Well, we look back at our variable, time is in days. So for 1 week, t would be 7. So we can say n is a question mark. We are not sure what that value is yet. And t is 7. Writing our formula, we have n equals 2,000 times 2 to the t. Subbing in the values that we know, we've got 2,000 times 2 to the 7. Now on our calculator, we can go 2,000 times 2 to the exponent 7, and that gives me 256,000 cells. For part B, we're asked how many cells were present 2 days ago. Now, if we're talking about the past, remember that that means we have a negative exponent. So t is negative 2. So n is a question mark, and t is negative 2. Writing our formula again, we have 2,000 times 2 to the t. Subbing in, we have 2,000 times 2 to the exponent negative 2. Once again, we can check this with our calculator. And that gives us 500 cells. Now, for this particular question, it may also be easy to do the math without your calculator. So we have 2,000 times 2 to the negative 2. So that means we have 2,000 divided by 2 squared, which is 4. So 2,000 divided by 4. Well, 20 divided by 4 is 5, and we've got those extra zeros, so 500 cells. So that's the last example in our lesson today. This is also the last topic in our unit. Hopefully now you've got a good foundation with regards to exponent laws, working with integral exponents, working with fractional exponents. You now have all the tools you need in your toolbox to take on more challenging and complex exponential expressions. All right, have a great day and we'll see you soon.